Okay, good afternoon, everyone. Thank you for coming to our talk, Don't At Me, Hunting Twitter Bots at Scale. My name is Jordan. I do research and development at Duo Security on the Duo Labs team.
And I'm Olabode Anishe, and I'm a data scientist in Duo Labs.
So Twitter and other social networks allow people to connect, to share ideas, and to build communities. InfoSec in general largely shares information via Twitter. Now, one of the things that makes social networks great is the ability to have authentic, honest conversations. Automated Twitter accounts or Twitter bots change this conversation. They change it both in good and bad ways, but regardless, that conversation is changed. So today we're going to see how we can go from zero to finding Twitter bots very quickly and at a large scale. So Twitter bots come in a variety of forms. These are the ones that many people are familiar with. That are spam-generating bots. They share the same links over and over in the hopes of having some victims click on the link and fall victim to the scam. Other bots don't necessarily generate content, but their goal is to try to amplify the popularity of either existing content or accounts. This could be done by liking or retweeting tweets or by following accounts at a large scale. So these don't necessarily generate spam, but they do introduce a level of dishonesty. And it's important to note that not all bots are malicious. We have bots that provide us with breaking news, geological information, or like the screenshot on the right shows, a stark reminder that this is truly the future, and we're living it together. So this research project didn't focus on whether a bot was malicious or benign. Instead, we wanted to ask ourselves, can we find a large data set and identify automation within it? So we're excited for the possibility of future research where we can take that next step, asking ourselves what makes a bot malicious. Now, while some bots aren't malicious, some are. The screenshot behind me shows a bot spoofing TechCrunch in an effort to try to spread what we call a cryptocurrency giveaway scam that we're going to talk about in detail later. Malicious bots aim to change the conversations that we're having, introducing dishonesty, spreading malicious content, and injecting themselves in the conversation to try to influence our discussions. Now, whenever it comes to hunting down bots, it's important to give credit where credit's due. There's an entire community of bot hunters already out there doing incredible work on finding bots and showing those results, and we've highlighted some people here today. So I'd encourage you, if you're looking for people to follow on Twitter, give these people a shout because they're doing really, really great work. Our goal today is to take that to the next step and to open up this research into a wider audience, you all. We're excited to be able to share our tools, techniques, and methodologies, showing how we can go from absolutely zero to gathering a data set and finding entire, not only Twitter bots, but botnets from those bots, and sharing that back with the community. We're firm believers that InfoSec is full of incredibly talented researchers who love taking on a hard problem. By researching Twitter bots, we're not only helping keep social networks healthy, it's simply a technically interesting problem to dig into. So we encourage everyone to take the research that we're producing today, build on it, improve on it, and really help take it to the next step. So whenever it comes to what we're going to talk about today, it's really divided into 2 or 3 parts. The first is that we want to gather a data set. This includes finding accounts, and then after we find accounts, we want to enrich that data set with content. This could be tweets that accounts are publishing, or the social networks for those accounts. Then we want to take a practical data science approach to build a classifier to try to identify bots within this large data set as accurately as possible. And finally, we're going to show how we can take a small number of bots and help tell the bigger story, using very straightforward techniques to try to map out connections and show how bots can be organized into entire botnets. So let's go ahead and get started. Now, whenever it comes to analyzing a data set, it really hinges on the data that you can gather. And so whenever it came to gathering our data set, we had 2 goals in mind. The first is that we wanted to play by the rules of Twitter's API. Twitter publishes an API, and we want our research to be reproducible both by academic and security researchers alike. This means that we used a single API key to gather all of our data. This also means that we're subject to the API rate limits in place from Twitter. This kind of leads us to our second goal, which is we still want to gather as large of a data set as possible, But since we're subjecting ourselves to the rate limits in place, we have to be as efficient as possible. We need to be clever with how we're using our requests, trying to get the most bang for our buck in order to get both a large data set very, very quickly. Now, this is what the data gathering process looked like. We talked about this just a minute earlier, but the first step is finding accounts. And what I mean by accounts are the screen name, the user ID, and metadata about the account. These are things like numbers of how many tweets you've published, how many people are in your social network. After we've gathered accounts, we can start enriching this data set, gathering the tweets and, where possible, gathering the social network information. So let's start by finding accounts. The first way we found accounts was using the Users Lookup API endpoint. This endpoint allows us to send up to 100 user IDs, and then for every ID that's valid, Twitter will return to us the full user object. Now, what's important to note about this endpoint is that it's incredibly quick. It allows us to make 900 requests every 15 minutes. And we talked about a full user object, but what does this look like? This is what a Twitter profile looks like through the lens of this API endpoint. As you can see, it's pretty much all the metadata about an account, where the only thing that's missing is the actual tweet content, or the actual information about who's following you and who you're following. But this information alone can be incredibly useful in identifying weird behavior, identifying bots that have anomalous characteristics. And we talked about this endpoint being very fast. So we can send 100 user IDs every request. We can make 900 requests every 15 minutes. Well, we did the math, and that results in us being able to make 8.6 million lookups per day. This is a significant data set, but it also poses a challenge to us. How can we generate account IDs that are valid in order to be able to take advantage of the speed that this endpoint offers? Let's talk a little bit about how Twitter account IDs are created. Twitter started creating account IDs as 32-bit unsigned sequential integers. Put simply, this means that we can start at 0 and work our way up, creating 100 IDs at a time, sending them up and seeing what comes back. Now, we didn't want to cover the entire 32-bit space because we just didn't have that much time. So instead, we opted to get a random 5% sampling. So for every 100 possible user IDs we could submit, we picked 5 random ones and submitted those instead. Now, it's important to note that this ID space isn't maxed out. Not every user has an ID, or not every user has the next ID in the chain. The density varies for multiple reasons. Maybe some accounts have been deleted, some accounts have been suspended, so you're not always going to have a one-to-one mapping. So the screenshot on the right shows what this density looks like. This may mean that for every 100 accounts we send up, maybe we get 80 back, maybe we get 40 back. It really just depends on where you are in that gathering process. Now, some papers have covered this before. Some papers have shown the 32-bit unsigned sequential integers. But what they don't talk about is that it actually goes a little bit further. Now, to put in perspective where we are data gathering-wise, just that first technique alone, over the course of a month, let us gather 66 million accounts. We notice that this account ID space moves into that 33-bit space, past the original 32-bit max integer. So we actually observed accounts all the way up to about the 5 billion range, and these accounts were created all the way up through 2016. This gave us another 3 million accounts to add to our data set. But then things changed. Twitter started generating IDs with a system they called Snowflake. Snowflake operates as a cluster of workers that all have the same job, to generate unique IDs as quickly as possible. Now, it's important to note that this format for IDs began to be used for all of Twitter's objects. So the same ID format is used for accounts, tweets, direct messages, likes, you name it. This, along with other reasons that we'll talk about in just a moment, makes it hard for us to enumerate Twitter IDs the same way that we did earlier. But first, let's see what a Snowflake ID looks like. Snowflake IDs are 63-bit IDs, with an example being shown at the top. We've broken out this ID into a binary format so that we can talk about how the pieces are organized. The ID starts with a 41-bit timestamp. This timestamp is based on a custom starting time, a custom epoch, of November 4th, 2010. After the timestamp, you have a 10-bit worker number, or a worker ID. This is a unique identifier for the worker who generated this ID. Now, we want workers to be able to generate many IDs per second or per millisecond, so they've also added a 12-bit sequence number at the end. This is a rolling sequence number that resets every millisecond. So now we would have to guess all of these values in order to come up with a unique ID that's valid. This is difficult. We would have to guess a timestamp, a valid worker number, and then the valid sequence number for that particular timestamp. This is difficult. Trust us, we've tried. You'll find in the paper some approaches that didn't pan out, didn't go the way that we thought they would. So even if we did generate a valid ID, we don't know if that's a valid ID for an account, for a tweet, or for a direct message. It's hard to get that same level of data gathering. So we have to take a different approach. Instead, we can let tweets and, by extension, users come to us. By hooking into Twitter's streaming API, we get a stream of tweets that are a random sample of public statuses. These tweet objects have the user object who happened to author that tweet. So this lets us stream in users over time. Now, what's cool about the streaming API is that it allows you to also do some targeted data gathering. You can put in keywords, locations, hashtags, topics, and more in order to refine what results are being returned to you. So if you're looking for a specific type of Twitter bot or a specific type of content, you can do this through the streaming API. Now, one thing we want to notice is that this does introduce a bias into our data set. When doing analysis over a data set, typically you want to take the same analysis and extrapolate it out, saying we can say this is part of the bigger picture. But you have to be careful in realizing what biases you're putting into your data before you can make those assumptions. In this case, the bias that we're putting in is that we're introducing users who have tweeted recently. This doesn't necessarily change things in the short term, but it's something that we have to keep in mind when doing the analysis later on. So we have a data set at this point of a whole bunch of accounts. Now let's start enriching the data. Let's start gathering the content. To fetch the tweets, we use the Statuses User Timeline API endpoint. This endpoint is slower than gathering users. In fact, it only allows us to make 144,000 requests compared to 8.6 million for getting users. So we have to be a little bit more careful with how we use it. We have to be a little bit more efficient. This means that we have to put some rules on what types of accounts we want to gather tweets for. The first rule that we put in place is that we want to gather only the latest 200 tweets for an account. We felt that this was enough tweets to try to indicate some type of bot-like behavior. Then we only fetch tweets for accounts that claim to have more than 10 tweets to begin with. You know, if they don't have enough activity to go off of, really it's a wasted request at that point. And then we filtered on accounts that had English as their declared language. Part of our analysis is manual analysis. English is the language that Olabode and I are most familiar with, and so it allows that part of the analysis to be as accurate as possible. And finally, many of the tweets that we gathered were replies. They were responding to a previous tweet. Twitter doesn't give us these by default, so we have to go fetch them. We went out and gathered the original tweets because that relationship between the reply and the original content has some very interesting characteristics that can try to indicate some bot behavior. So after gathering tweets, we can start talking about mapping out social networks. The screenshot on the right shows how we were able to take one bot account, which was a fake follower, and we were able to do a 1-degree crawl, getting every account that bot was following, and then likewise, every account following those accounts. This let us create a mapping showing thousands of bots, all with the same characteristics, all following the same legitimate accounts. Now, so this is an incredibly powerful tool, and we'll talk a little bit more about it later. But what's important right now is that this is very, very slow. The API endpoints that we can use to gather this data only allow about 1,400 requests per day. This means that it's simply infeasible to do this across our entire large data set. But instead, as we'll see a little bit later in the presentation, doing targeted social networking analysis can be extremely powerful in taking a small number of bots and finding entire botnets from them. So this is what our overall data gathering system looked like. We're not going to cover every box and every arrow in the flowchart, but really there's the two parts to the system. There's gathering accounts and gathering tweets. And we talked about speed. This is what this looks like in summary. Gathering accounts by far was the quickest operation. We could submit up to 8.6 million lookups per day, and that's not counting the accounts that we get from the streaming API. Gathering tweets was much slower at 144,000 requests per day, with gathering the social network at the end being so slow that it's infeasible to do this at scale. This is our final data set. These are the final numbers that we have to start analysis. Over the course of a month, we are able to gather 88 million accounts, enrich 3.1 million of those accounts with the tweets that they authored. This gives us a final data set of 576 million tweets. So at this point, we have a significant data set and we can start analysis. I'm going to pass it over to Olabode to talk about how we can take a practical data science approach to identify bots within the data set.
Thanks, Jordan. So before we can go about trying to classify these different types of accounts, we need to try to understand, what do bots look like? And so we're going to talk about that through the data that we were able to gather. So like Jordan mentioned, we have three types of data. We have the account attributes. Again, those were the counts that you have. Those number of favorites, number of tweets, how many times your account has been listed, and how many tweets an account has authored. Then you have the actual tweet content. So this is what's actually in the body of a tweet. Are there URLs? Is there media? Do they mention someone? Things of that nature. And then last, you have the tweet behavior. Looking at the way someone tweets can say a lot. Are they tweeting throughout the entire day? What is the distance between the reply of the user ID that they're actually replying to, and things of that sort. So the first step we tried to do was try to develop some heuristics. We didn't want to do anything sophisticated at first because it may not be that necessary. And so we tried to examine these particular attributes by themselves, trying to find outliers after looking at the distributions. So looking at the account attributes, we looked at a few things. The first thing was the entropy of a username. If you're trying to create accounts in mass, maybe you're going to just generate a random user. And so as you can see on this slide, there's a username that seems pretty random. There's a great mixture of numbers and letters. This was associated with a bot account. We also looked at how many numbers are at the beginning and the end of a screen name. Again, if maybe you have a set number of screen names that you use, and maybe you just want to increment for every bot account that you create. And then the last two really fall on two different ends of the spectrum. We're looking at the ratios of followers to following. If someone's only following accounts, like a fake follower, maybe that ratio will probably be really low. But maybe if they're trying to masquerade or appear to be a legitimate account, maybe that ratio would be a lot higher. So the same thing could be said about the number of tweets and the number of likes. There are accounts that are kind of sleepless and that they author a lot of tweets or spamming, and they also are liking a lot of accounts. And then there are some that have no activity at all, really. But then we have the tweet content. Again, like I mentioned earlier, this is like the number of hashtags or the percentage of tweets that include media or URLs. The thing about this particular set of attributes is it presented a couple of problems. Like we mentioned earlier, there were accounts that just tweet out links that may be a little bit malicious or try to get people on a particular insecure site. But then there are a lot of legitimate accounts that are tweeting links to their content or their articles, like legitimate news organizations. So that's kind of the problems of actually looking at these dimensions by themselves and not taking a more holistic view. Then we have the tweet behavior. The first thing that we looked at was the number of unique sources. So the source is an attribute that's returned into the tweet object. This contains information of like where the tweet was authored. Was it Twitter for iOS or Twitter for Android or some other type of application? You would expect that most users would probably have maybe 1 to 2 unique sources. But for those people who are maybe authoring tweets from maybe 5 sources or particularly unique sources that we've never seen anyone else author tweets from, that may be pretty suspicious or weird. Then we have like the time to reply and to retweet a particular tweet. And this is why it was really important to gather those replies because, again, that wasn't included in the original tweet object. It's really hard for a human being to look at a tweet, come up with a reply, and then actually to reply in about 5 to 10 seconds. Maybe that is a sign of automation. And the same thing can be said about retweeting a tweet in a very quick time span. We also looked at the number of unique users someone was retweeting. It would be pretty weird if they were only maybe retweeting their own tweets or someone else's tweets, because we expect that most people are retweeting a lot of different accounts with a lot of different material. Then we also looked at the distance between geolocation-enabled tweets. We were thinking that we would find some people or some accounts that are tweeting from locations in really rapid manners where they would maybe have to travel at light speed to get from location to location. The one problem with this particular dimension is that it's pretty sparse and that not a lot of people have the geolocation enabled for all of their tweets. And lastly, we looked at the distribution of tweet times, or like how many hours out of a day was a user actually tweeting. And so you can see in the graph on this particular slide, we see a genuine account and an account that was a bot that identified itself as such that just tweeted song lyrics. You can see that there's a pretty steady or uniform distribution on the number of tweets authored every hour by the song lyric bot. Again, those accounts are sleepless in nature. But the genuine account, you see there's some spikes in like a trough that's like 6 or 7 hours. We hypothesized maybe this is just the user actually sleeping and actually not authoring tweets. But again, we would suspect there'd be some differences between people or accounts that are utilizing automation and those accounts that aren't. The big thing is that many bots try to be or appear to be human. And we really broke those down to 3 different types of bots. There's the spam bots that we talked about earlier, those that are just putting a lot of content onto Twitter's platform. They're spamming this text or media or links. Then we have the fake followers. These accounts are really trying to amplify the popularity of a particular account by increasing the ratio of followers to following. That gives a lot of air of legitimacy to an account. And then there's accounts that we classified as amplification bots that try to increase the popularity of a particular tweet by liking or retweeting said tweet. So now that we've kind of talked about some of the different attributes that are associated with bots and the different types of them, what we want to do is actually look at all of those dimensions together, try to weight them appropriately and trying to find and identify bots. And this is really why we wanted to use machine learning to try to do this at scale. So I understand that we have limited time up here, and I can't explain the entire data science process or what it means to be maybe a machine learning engineer. But I think it's important to kind of level set, to bring everyone to the same level and kind of introduce some of the process and some of the terms that I'm going to have later in this presentation. So the first step usually in any data science project is to gather or acquire the data. Jordan led that part, and I consider that the pretty difficult part of the entire process. Then you want to build features. So like we talked about earlier, the identifying characteristics of those bots are going to be translated into our features that we're going to feed into our algorithm. Then we also want to split the data. And it's important that your data that you have and you're splitting, that you're going to train your model on, actually has labels. So can you have some type of certainty that that account is actually a bot account? And we'll talk about our data set in a couple slides. Then you want to evaluate different algorithms. There are many algorithms that can help you classify or do binary classification, and we chose a few. And then you want to test your model on unseen data. You want to see how well your model is going to generalize to data that your model hasn't been trained on. So now that we have the process, I'm going to introduce a few terms that I think will be helpful as well. So I've mentioned already we have models and algorithms. So the algorithms are really the math associated with trying to classify accounts. Those models are those trained algorithms that have been trained with some type of training data. We have 3 particular algorithms I'm going to explain a little bit further. The main thing I want you to remember is that these algorithms output a probability that an account is a bot. So it may be 51% or maybe 75%. That's the main thing that you want to take away. These particular algorithms, decision trees at first, use it like a if statement logic. So if this, then that. And they use that and maybe branch in different ways to try to classify accounts. Random forest builds on that by using a lot of decision trees. That number is configurable. And they branch in different ways to try to take advantage of those economies of scale. And then we have another algorithm called AdaBoost. It learns from weak classifiers like decision trees, and then builds another model to learn from the mistakes that it was making to try to have a higher accuracy. The main important thing is that to try to evaluate or to understand how your model is performing, we have usually 2 particular metrics that are important in binary classification. We have precision, which is trying to understand of all the accounts that you labeled, in our case, as bot accounts, how many of them were actually bot accounts. And then we have recall, which is of all of the bots in your data set, how many did you predict? And last, we have cross-validation, which we're going to talk about a little bit further in a step-by-step process. But it's a process of trying to evaluate how your model performs by splitting the data in different ways to see what are the metrics like precision and recall. Now, for the data scientists or the ML engineers in the audience, I know I probably grossly oversimplify this entire process, but I just wanted to give everyone a brief overview. So this is the data set. So the data set that we actually trained our models on consisted of partly some data that was gathered by some USC researchers in a paper that was released back in 2016. Again, these are the labeled accounts that were labeled as genuine. They reached out to users and actually interacted with those accounts, and then accounts that were labeled as social spam bots or just bots in general. But as we said earlier, we identified some bots that were associated with the cryptocurrency giveaway scam. So we were able to bolster our data set by adding those accounts too. So now I'm going to talk about how we end up doing some classification by looking at just the account features and also including that tweet data, that enriched data set. We're going to talk through how you go about finding the best model and also about how to go about identifying the most relevant or features that give you the most signal. So in order to find the best model, usually again, like you start with maybe a lot of models or algorithms. And again, those algorithms have different parameters that you can change. But again, we didn't do any of that. We just started with 5 algorithms, 3 that I mentioned earlier. After you do that, again, you split the data. So again, you want to see how if you shuffle the data, does your model perform differently? And what are the attributes of those particular accounts that did perform well on? And then again, we use those metrics that we talked about earlier. And that helps us evaluate or choose the best particular model to then predict on these unknown data sets. So this is accuracy. Again, we mentioned precision and recall, but accuracy is something that most of us understand pretty well. As you can see, the 3 particular algorithms that I talked about earlier perform very well, above 95%, really in most cases 98%. The model that performed the best was the random forest model that I mentioned earlier as well. As you can see, it was still pretty close to AdaBoost, but on the other metrics that we tried to evaluate these algorithms, random forest was far above the best. So these are some of the other metrics that we had, again, associated with precision and recall for this random forest model. We saw that our model had 99% precision and 97% recall. So it was doing really, really well. But we want to underscore that classification is really hard. I'm going to talk a little bit more about that, especially in the concept of doing this analysis on this Twitter data set. What we want to stress is there are a lot of unknowns. We don't know the true percentage of bot accounts that are actually on Twitter's platform. And that makes some of the analysis really hard, especially something associated with calibration. So I'm going to take some time to explain that. So calibration, like I told you, each model outputs a probability that an account is actually a bot. So if I say that an account has a 75% probability of being a bot, we would hope that 75% of accounts associated with that probability would actually be bots and 25% wouldn't be. Now, calibration is not always important with doing classification, but it does go into actually, if you wanted to make a decision or action on whether you want to block or maybe restrict an account, that would be pretty important. The next thing we want to talk about is we in our data set only have 2 types of bot accounts. There are many other types of automation on Twitter's platform that we didn't have. So it would be particularly hard to generalize our results because we might be missing bots that are in our data set. And then last, we don't have the optimal thresholds. So our models, when trained, use 0.5 as the barrier of whether an account is a bot or not. So again, if an account has a 51% probability of being a bot, we label it as a bot account. And if it was 49%, we would label it as a genuine account. Now, it's hard to understand if that is the optimal threshold in order to make prediction. And this would definitely skew our results if that percentage is not actually the percent or proportion or makeup in our unknown data set. So I want you to kind of keep in mind some of these problems associated with classification, trying to understand how difficult it can be. But we actually try to do our best to try to resemble what we believe to be or what people have reported on being the true percentage of bot accounts in there. Those same USC researchers talked about maybe the percentage being between 10 and 15, maybe at those are at the lower ends. But we wanted to try to mimic those data, that particular proportion, and put that into our data set and see how our classifier actually performed. So as you can see, those percentages are a bit lower than the 99% precision that we had earlier. We have 92% precision when only 10% of accounts are actually bot accounts. And that rises to 94 when we're estimating that 15% of accounts are actually bots in our data set. Now, people are probably wondering, what is the number associated with the accounts that we actually gather with 88 million accounts just utilizing the account attributes? So our classifier, using again that 0.5 or the 50% probability threshold, found that 32% of accounts were more likely to be bots than not, but only 1% had that over 90% probability. A lot of the accounts had a probability that was in the middle, that between 0.4 and 0.6. So it's possible that those accounts, some that were classified as genuine accounts, could have been actual bot accounts, and those that are actually labeled as bot accounts could have been genuine accounts. So that's just one thing to keep in mind. And here's like the makeup or some of the attributes that we looked at, and what was the makeup of those accounts that were more likely to be bots and ones that weren't. So when really just examining the ratio of followers to friends, those accounts that were least likely to be bots had a higher ratio. And just to drive this home, all of the accounts that were verified in our particular unknown data set, this unlabeled, were all in the non-bots or genuine accounts. So this is why this particular number would be skewed and be higher. When it came to screen name entropy, we didn't really see any differences, especially not any statistically significant differences between those accounts in the top 20% and the bottom 20%. However, when we looked at those accounts when we looked at the numbers at the beginning and the end of the screen name, we did see some pretty unique differences between those accounts that were labeled as bots and not. But also we saw that our classifier was actually saying that accounts that were more active, that were tweeting or liking tweets more often, were more likely to be genuine. What we want to stress is that your model is only as good as your data. So we talked about how our particular data set doesn't include all types of bots. And so we want to drive home the problem associated with trying to classify other types of automation that you may have never seen before. So our model only had an 80% accuracy when trained with those social spam bots, but trying to predict those cryptocurrency giveaway accounts. And when you flip that, our model barely was only barely better than a coin flip when trained with the cryptocurrency giveaway bots and trying to predict on the social spam bots. Again, when these bot accounts have differences or their accounts are not the same, your accuracy is going to decrease. But the great thing is we don't just have to look at the account attributes. We can add the tweet content, the behavior data, and we hope that would actually increase the model's precision, accuracy, and things of that sort. So in total, we had about 22 features after we iterated and the ability to actually build those features with the data that we had. Now, it's important to note that thousands of features could probably be created according to Twitter data, but these are the 22 that we had. The one thing that's important, though, again, is all these features aren't created equal. I talked about the sparsity in the data being a problem. But another thing is when you have fewer features, you have less data to store. Your model has less complexity, and it's usually faster to train. And that's important when you're trying to do these things at scale. So in order to try to find those features that were the most important or that provided the most signal, we use recursive feature elimination. So there are many ways that you can go about eliminating features, but this was the approach that we took. And so utilizing this approach, we found that these were like the 5 most important features of those 22. Is an account a default profile? So those are those egg accounts that don't have a picture and they have the default bio. Also, we looked at the average number of users that were mentioned in a tweet. So are they replying to tweets? Do they have tweets that just mention other users? Then also we looked at the average number or average distinct hours tweeted in a day. So again, we talked about those restless accounts. We of course hypothesized, and our model actually showed this out, that it tried to find users that had those high numbers. We also looked at favorite rate and also the distance between the user's particular user's ID and the ID that they were replying to. So we found that our model was actually better with this particular data as we hypothesized. And here are some of the results on that unknown data set, that large corpus that was enriched with those tweets. We found that our model that was more accurate only found that 21% of accounts were more likely to be bots than not, and only 0.8% had above that 90%. And so we want to kind of drill down and make sure that everyone understands, like, this model was better, it had better accuracy, and so that's why that number was lower. And so again, to kind of compare those particular attributes that it found that was pretty successful in help identifying bots or not, we looked at those accounts that had the highest percentages. They had more default profiles than those in the bottom 20%. They also mentioned users less. Those bot accounts also tweeted more often. They actually were favoriting less tweets. They were less active on the platform. But also, even though those numbers are very large, they're pretty similar, really. And so we didn't really find any big differences between the average reply ID distance. But we want to, again, say that classification is hard, even if you have the context and the tweets. But more data can help. So again, when trying to identify bots of a different type, we saw that our models improved. Again, We're going from 80% to really 83% when our model was trained with the social spam bots and predicting on those cryptocurrency giveaway bots. And then our model actually increased from 53% to 62% when our model was trained with the cryptocurrency giveaway bots and then predicting on the social spam bots. Now we want to talk about some of the limitations or some challenges associated with our approach and the data that we had. It's important that we kind of provide this context and perspective. Accounts change over time, so we only were able to pull the last 200 tweets. So if an account was exhibiting characteristics of automation in the tweets before those 200, maybe we'll misidentify a particular account. Also, we don't have that network or those connection data that Jordan talked about being pretty slow to gather. That would really be able to tell us a more holistic view of how that account is interacting with other users and the platform in general. And lastly, we don't have the insight into the cost of a false positive. That's a very big deal, especially when you're doing any type of prediction, because that would probably change your threshold and also would change, again, the metrics associated with precision and recall. Again, if a false positive is particularly costly in terms of the user experience or support costs, again, you might want to move that threshold that you're pretty sure that an account is actually a bot before you take any action. But what we want you to take away is that straightforward techniques do help find bots. We didn't invent a new machine learning technique or really changing the parameters associated with the defaults for these particular algorithms, but we were able to identify bots with a high accuracy, precision, and recall. So now that we've identified some of these bots or accounts that have a high probability of being bots, can we find some connections? Can we find a larger botnet? And Jordan's going to talk about a little bit about that.
Awesome. Thank you, Olabide. So we've gathered the data. We've taken a very practical data science approach to identify bots within that data set. Now we can talk about the final chapter in the story, which is how do these bots that we identify connect with one another? How are they organized? How are they structured? And how do they work together to share a common goal? During the course of our research, we identified accounts that looked like this. Many of you may have seen an account like this. Some of you may have been spoofed by an account that looks like this. These bots were spreading what we call a cryptocurrency giveaway scam. The premise of the scam is very simple. They'll take a legitimate account, starting with legitimate cryptocurrency accounts like Bitcoin. They'll wait for Bitcoin to tweet, and then they'll interject themselves into the conversation, saying, as part of this great news, we're excited to share a new giveaway with our viewers. And then they'll say, if you give us so much cryptocurrency, we're going to give you back even more. Now, I understand it seems foolproof, but they do in fact take the money and run. Now, what makes these bots so effective is that they spoof the legitimate account. They copy the profile picture, they copy the name, and they try to make it seem as if they're legitimate. We wanted to ask ourselves, how can we see the links between these bots? How are they structured? How are they operating? So we turned to their social networks connections. One of the first things that we noticed was that many of the bots all followed the same seemingly legitimate accounts. We didn't see any clear ties to why these accounts were being followed by all these bots. We didn't see a clear tie associating them with the scam at all. But what we did know is that all of these accounts had a whole bunch of bots following them. So we can start mapping this out. We can say, let's start with a small number of bots, figure out who they're following. For every account they're following, let's find more bots and just start working our way through. For every new bot we find, we expand our network. Running this recursive crawl gave us two clusters that we wanted to point out today. The first cluster is that hub and spoke structure that we talked about just a little while ago. In this structure, you have all of those legitimate accounts that are highly connected nodes towards the bottom left, those very dark nodes. Around them, you have all of the bots that are following them. So that was one structure that we found. The next cluster that we found took a different approach. It was more of a mesh-like structure. So instead of bots following legitimate accounts, instead they opted to follow each other. Now this is visually compelling, but it also helps us tell a story. We're able to show how the structure of this botnet evolves over time, changing the way that they're organized. Let's take it a step further. To add legitimacy to the tweets, the bot owner created separate bots that had one job, and that was to like the tweets associated with a scam. This is called amplification. This is trying to give an artificial inflation to the popularity of a tweet. So that if I'm a victim and I'm scrolling through Twitter, I'll come across one of these scam-related tweets. I'll see that it's been liked or retweeted multiple times, and maybe I'm less inclined to be suspicious. These are what those accounts look like. This is a traditional amplification bot. In this case, you'll notice that the bot was created in June of 2018. I think that we found it probably around June of 2018. And it had one job, and it liked tweets. Every one of those likes was a tweet associated with a scam. So we can start crawling these as well. We have statuses of bots that we found already. Let's figure out who liked those tweets. For every one of those accounts that liked those tweets, let's find every tweet that they've liked, and let's find new bots from those connections. Mapping out all of these relationships helps us tell the whole final story. On the left-hand side, you have that original hub and spoke structure that we talked about. And then on the right-hand side, you have that more mesh-like structure of bots. But the glue that's keeping everything together are those amplification bots. Those green relationships are the likes, where someone is liking a tweet from that particular bot. This helps us figure out that this botnet has a very hierarchical approach that's more sophisticated than what you would see with a traditional botnet. Usually, every bot does the same job. They all spread the same spam in the same way, and it's very flat. But in this case, we saw a hierarchical organization here that in fact changed and evolved over time. One of the first ways that the bots changed was through the content. They would add, remove white space. They would change letters in the tweets, say taking the letter N and replacing it with the letter N from a different Unicode character set. Visually, it's going to look the same, but if I'm trying to do some string matching, it's simply not going to work. They also changed who they're targeting, who their target audience was. We talked about cryptocurrency accounts, but we've also seen many instances where they changed techniques and started spoofing legitimate news organizations, including Wired, CNN, and TechCrunch. And this helps show what you see from a victim's perspective. You see a legitimate tweet at the top, followed by the scam right below it. Towards the end of our research, after the paper was completed and we were still monitoring the botnet, we found something interesting. We found close to 10 verified accounts being taken over and used during this scam. Now, the screenshot on the right shows what this looks like. You see an account that's spoofing Coinbase. And while we've blurred out part of the screen name because it is an innocent account, you can see just from the first couple letters that screen name is not Coinbase. But since it's a verified account, it adds an air of legitimacy to the scam, where if they're replying and interjecting themselves into a conversation, it's going to be more difficult for me as a potential victim to be able to tell the scam apart from a legitimate conversation. To really illustrate this point, this is what it looks like in a conversation. You have legitimate Elon Musk account at the top replying to a user on Twitter. Immediately below it, you have a verified account that's been taken over, uses Elon's profile picture, changes his name, and spreads the spam. Now, in this case, as a potential victim, I really only have a couple things to go off of. I mean, the verified check mark is there, but the screen name is different, so maybe I could catch that. And the S in Musk has been changed to a different character set that's a Unicode equivalent. It's kind of hard to tell from back there, right? Imagine if you're just scrolling through Twitter, trying to have conversations, trying to see what people are doing, you would see that this seems legitimate. It's easy to fall victim to it. And finally, at the very bottom, you still see the same amplification that we talked about earlier with the likes and the retweets. Now, after we finished the research and we published the results just yesterday, a couple days ago, we had some people commenting about it and helping kind of get the word out, which was always exciting from a researcher's perspective. In this case, someone was sharing the research, and then they actually had a bot that was spoofing their account, spreading the same scam, respond to that tweet, trying to, yet again, spread the scam. So a little bit of irony at the end of the project. So we've shown how straightforward techniques can really allow us to follow a thread, unraveling an entire botnet. This is an application of targeted social networking mapping. It's nothing more than that allows us to take a small number of bots and tell a bigger story. Now, we believe in honest and transparent research. That's the core of what we do. And so at this point, we shared everything with Twitter, giving them our findings, our methodology, and gave them access to our data set. We had a very healthy conversation with Twitter. We enjoyed being able to share our work with them. And we're excited about the different things that they have coming out that they've published in blogs just here in recent months. they shared with us this statement. Twitter is aware of this form of manipulation and is proactively implementing a number of detections to prevent these types of accounts from engaging with others in a deceptive manner. Spam and certain forms of automation are against Twitter's rules. In many cases, spammy content is hidden on Twitter on the basis of automated detections. When spammy content is hidden on Twitter from areas like search and conversations, that may not affect its availability via the API. This means certain types of spam may be visible via Twitter's API, even if it's not visible on Twitter itself. Less than 5% of Twitter accounts are spam related. Now, we're excited to continue this conversation, exploring not only new areas of this research, but also exploring what is that relationship between what's exposed via the API and what's exposed via the UI. But we also want to give back to you, to the community. And this is why, as part of this project, we're open sourcing the code that we wrote to do this research. This includes the data gathering system, the code that we use to build the features, an example showing how those features can be used to create a model to identify Twitter bots. We're also sharing our paper. This paper includes the full methodology of how we did this research project and all the findings associated with it. And in summary, large Twitter data sets can be gathered very quickly and very efficiently if you're efficient with how you use the API requests that you're given. Then you can take this data set and you can apply a very practical data science approach to accurately find bots within this data set. Then you can take these bots and you can start unraveling entire botnets, figuring out how they're organized, how they're structured, and how they work together. And it's easy to stand on stage and say this is the conclusion of the research, there's nothing else to explore. We're taking the complete opposite approach. We're excited to be able to open this up to the community, lowering that barrier to entry to start hunting down Twitter bots. By working together as a community, we're excited to see how people build, improve, and find new ways to identify bots at a large scale. By working together, we can create healthy social networks that allow us to share ideas, connect with one another, and build really healthy communities. Thank you.